Hello everyone and welcome back to the Calculus 1 video lecture series. Today we are going to be looking at how to find a limit algebraically without the use of a table or graph. So there are a number of different techniques that are used to find limits algebraically, and the technique that you use actually depends on the type of function. And I will say that we will revisit limits later on in the course, and we will be finding limits algebraically later on in the course once you have a little bit more calculus background. So for now, the technique that you're going to use really depends on the type of function. Now remember, if you get a 0 in the denominator, yes, the function is undefined. However, if you get a 0 over 0, a 0 over 0 is what is called an indeterminate form. 0 over 0 does not equal 1. It does not necessarily mean that the limit does not exist. It just means that you need to do more work to find the limit. So before we really get too far in depth with that, we need to go over what are called limit laws. And these limit laws look a lot more complicated than they actually are. So for the first one, let's say that you have a sum that is inside of a limit. Then what you can do is you can separate it into the sum of two separate limits. Same thing with differences. If you have a difference inside of a limit, you can split it up into the difference of two separate limits. This means that if you have a function with more than one term, you can simply take its limit one term at a time. If you have a constant multiple inside of a limit, it can come out of the limit and be written outside as multiplication. If you have a product of two functions inside of a limit, you can write it as the product of two separate limits. Now you can do the same thing with quotients up to a point. So if you have the limit as x approaches a of f of x divided by g of x, you can break this up into the limit as x approaches a of f of x divided by the limit as x approaches a of g of x. So you can just take the limit of the top and the limit of the bottom as long as the limit on the bottom does not equal 0. And as long as you don't get a 0 over 0 either. But as long as the denominator does not equal 0, then you can do this. Now, if you have the limit as x approaches a of some function f of x raised to a certain power n, then what you can do is you can just take the limit of that inside function and then take that limit and raise it to that outside power n. And you can do the same thing with fractions, fractional powers, or square roots, for example. You can just take the limit of the inside function and then raise it to that power. So I'm not going to tell you what f, g, and h are for this next example, but what I am telling you is that the limit as x approaches 2 of f of x is equal to 4, the limit as x approaches 2 of g of x is equal to 5, and the limit as x approaches 2 of h of x is equal to 8. What we're going to do is we're going to find limit laws for each of the following. So we're going to find the limit as x approaches 2 of f of x minus g of x over h of x. So the quotient law for limits says that we can just simply take the limit of the top and the limit of the bottom. And in the limit of the top, the difference law for limits also says that we can split up a difference inside of a limit into the difference of two separate limits. So I'm going to break this down into the limit as x approaches 2 of f of x minus the limit as x approaches 2 of g of x. Also, I'm very sorry about that. My stylus does glitch out once in a while. I don't know how to fix it, and I don't know why it does it, so I do apologize for that. That will happen once in a while. And then we're going to divide that all by the limit as x approaches 2 of h of x. So the limit as x approaches 2 of f, that was given as 4, minus the limit as x approaches 2 of g, which was given as 5, divided by the limit as x approaches 2 of h, which is 8, giving us a final limit of negative 1/8. So what I want you guys to do is I want you guys to try these next two. Use limit laws to evaluate each of these limits. So go ahead and pause the video and evaluate each of these limits. Okay, so for this next one, for the limit as x approaches 2 of 6 times f of x times g of x plus h of x. Well, constant multiples can simply be pulled outside of the limit. And if you have a product inside of a limit, you can split it up into the product of two separate limits. So I'm going to write this as 6 times the limit as x approaches 2 of f of x times the limit as x approaches 2 of g of x. And the sum law for limits says that we can break up a sum inside of a limit into the sum of two separate limits. So I'm going to add to that the limit as x approaches 2 of h of x. So that gives us 6 times that limit equals 4 times that limit equals 5 plus that limit equals 8 gives us a final limit equal to 128. So then for this last one, for the limit as x approaches 2 of g of x to the third power, what we can do is simply take the limit as x approaches 2 of that inside function g of x, then take all of that and raise it to the outside power 3. So the limit as x approaches 2 of g is equal to 5. Then 5 raised to the third power gives us a final limit of 125. Now what we're going to do before we get into the algebraic techniques is I want you guys to find one last limit using a graph. So what I want you guys to do is on a graphing calculator, I want you to graph f of x equals x squared plus 1. And I want you guys to use that graph to find the limit as x approaches 3 of f of x. And I want you guys to look at the relationship between this limit and the function's value at 3. So take a minute, pause the video, and look for that relationship. All right, so this limit, as x approaches 3 of f of x, this limit is actually equal to 10. And you will notice that this is the exact same as f of 3. So this was one of those instances where the limit actually did equal the function's value. And the reason is if you look at the graph of x squared plus 1, there's nothing weird going on here at 3. There's no holes, there's no jumps, there's no asymptotes, there's nothing weird here. It is a smooth, unbroken curve here at 3. So that is why there was no difference between what the function was approaching and what the function was actually doing at 3. So in a case like that, the limit equals the function's value. And you will actually find that that always happens with polynomials. So anytime that you have a polynomial and you're taking the limit as x approaches whatever value a, all you have to do is evaluate that polynomial at x equals a, and then that is going to be the limit. This is a technique called direct substitution. Direct substitution, when you're taking a limit, just involves you plugging in that value directly into the function and seeing what happens. In the case of polynomials, because they are always smooth, unbroken curves, the function's limit will always equal the function's value. So anytime you have a polynomial, all you have to do is do direct substitution, and then that will be your limit every single time. Now, rational functions, which are just quotients of two polynomials, you can do the same thing. You can use direct substitution when you have a rational function, as long as the denominator does not come out to 0. So if you're taking the limit as x approaches a of some polynomial p of x divided by some polynomial q of x, that is going to equal p of a divided by q of a, provided that q of a does not equal 0. So direct substitution will work to evaluate limits of rational functions as long as you don't get a 0 in the denominator. And in fact, direct substitution is a legitimate limit technique, and you should always try direct substitution first. So I don't care whether it's a polynomial or not a polynomial. I don't care how gross the function looks. Always try direct substitution first, no matter what. That involves you plugging that value of that limit directly into the function and see what happens. If you get a real number, if you plug it in and get a real number, congratulations, your limit is done. That is the value of your limit. This is always going to work for polynomials, and it might work for other types of functions. So if you do direct substitution and get a real number, that's its limit, and you can move on. Now, for polynomials, because you never have a situation where the left limit and the right limit don't equal, they're always smooth, unbroken curves, you can use direct substitution for even one-sided limits if you have a polynomial. So what we're going to do is we're going to use direct substitution to evaluate each of these. And if you want to attempt any of these before I start them, just please pause the video right now and resume when you are done working. So for the limit as x approaches 3 of 1/2 x. 1/2 x is a polynomial, so we are going to do direct substitution. We get the real number 3/2. So because we did direct substitution and got a real number, that is our limit. Now for this next one, if it helps, you can go ahead and draw a graph for the limit as x approaches 2 of 6. Well, the function y equals 6 is a horizontal line. So as x approaches 2, either from the left or from the right, you're going to be approaching the y value of 6. So the limit as x approaches 2 of 6 is equal to 6. So the limit of a constant is always itself. And then for this last one, for the limit as x approaches 1 from the right of 7x cubed plus 3x squared plus 4x plus 2. Because this is a polynomial, you can use direct substitution even if you have a one-sided limit, because the limit from the right, limit from the left, limit from both sides, they're all going to equal the same thing. It's a smooth, unbroken curve. So all you have to do for this one-sided limit is just direct substitute 1 into every single spot that you see in x, plus 2, and you get 16. So then, because you direct substituted and you got a real number, 16 is what your limit is equal to. So you should always try direct substitution no matter what the function is and no matter how bad it looks. So for the limit as x approaches 2 of 3x squared minus 4x over 5x cubed minus 36, let's try direct substitution and see what happens. So we're going to have 3 times 2 squared minus 4 times 2 divided by 5 times 2 cubed minus 36. And when you evaluate all of this, you get 1. So because we direct substituted and we got a real number, our limit is equal to 1. And then for the last one, I've got the limit as x approaches 2 of this disgusting function, so I'm just going to direct substitute and see what happens. So I've got the square root of 2 times 2 cubed plus 9 plus 3 times 2 minus 1 all over 4 times 2 plus 1. And when you actually compute all of this, you get 10 over 9. 10 over 9 is a real number. So because we direct substituted and got a real number, our limit is equal to 10 over 9. So direct substitution is always something that you should try every single time. Now, if you direct substitute, even if it's obvious that the denominator is going to come out to 0, you should always take a moment to direct substitute into the numerator as well. Because I will say right now that 0 over 0 is treated a lot differently than any other number over 0. We're going to get into things like 5 over 0 later, but if you get a 0 over 0, that is an indeterminate form. What that means is that there is some common 0 in the numerator and denominator that's not canceled out, such as a common factor. So one thing that you can try is factoring the numerator and denominator, finding that common factor and canceling out that common factor. It doesn't mean that the function is defined at that point in question. It just means that the limit actually exists, and this is a technique that you will use to find that limit. If this technique works, then that limit exists. Now, if you have a radical, another technique that you can try is rationalizing. So, at this point in the course, there are only two ways to handle a 0 over 0, factoring or rationalizing. There are other ways to handle this. We're going to get to those later on in the course, but right now, in Chapter 2, I promise that any limit that comes out to a 0 over 0 can be fixed by either factoring or rationalizing. So what we're going to do is we are going to evaluate each of these. Now, you should always, even if it's just mentally, try direct substitution first. So for this first limit, I'm going to direct substitute 2. So 2 squared minus 6 times 2 plus 8 gives us 0. Over 2 squared minus 4 gives us 0. So an initial direct substitution gave us a 0 over 0. So what that means is that we are going to try factoring both the numerator and denominator and seeing what happens. Now, until you are actually ready to direct substitute, you cannot drop this limit notation. So if all you're doing is factoring, you do need to keep that notation, the limit as x approaches 2. And let's try factoring the numerator and the denominator. So the denominator is a difference of squares. It factors as x minus 2 times x plus 2. And then for the numerator, we're looking for two numbers that multiply to positive 8 and add up to minus 6, which is going to be minus 2 and x minus 4. So you can see the common factor x minus 2, so I'm going to cancel out that common factor of x minus 2. So after we've simplified, that will give us a limit as x approaches 2 of x minus 4 divided by x plus 2. So now that you have fully canceled out that common factor, let's try direct substitution again. So we'll get 2 minus 4 all over 2 plus 2. And then that will give us negative 1/2. So because we just direct substituted and got the real number negative 1/2, that means negative 1/2 is now our final answer. So I want you guys to try this next one here on the top right, the limit as x approaches 5 of x squared minus 7x plus 10 over x minus 5. So go ahead and pause the video and try this next one. Okay, so you should always start by direct substitution. If you direct substitute, you get a 0 over 0. So I see a couple things here that look like they can factor. Looks like we can factor the numerator. So again, I'm going to leave the limit notation here. I'm going to factor the numerator. So the numerator is actually going to factor as x minus 5 times x minus 2. And then I am going to put parentheses around that x minus 5 in the denominator. So you can see the common factor is x minus 5, so I'm going to cancel out that common factor, giving us the limit as x approaches 5 of x minus 2. After you simplify, you should try direct substitution again. So we're going to get 5 minus 2, which gives you a final limit equal to 3. So now that our direct substitution finally resulted in a real number, that is what your limit is equal to. And then for this last one, if you do direct substitution, you get an undisputable 0 over 0. And there's nothing to factor here. But I do notice that there is a square root in the numerator. So what I'm going to do is I am actually going to rationalize the numerator. So I'm going to multiply the top and the bottom of this fraction by the numerator's conjugate, which is going to be the square root of x plus 1. Whatever you do to the top, you need to do to the bottom. And what I would recommend you do is fully distribute and simplify the numerator, but leave the denominator alone, because the whole point of this is to try and find that common factor and cancel it out. So while I know that you were fully trained to distribute everything, I will say do not distribute the denominator, because if you leave the denominator written as multiplication, If you have a common factor with the numerator, you will be able to find it and cancel it out. If you distribute the denominator, you're unfactoring it and you won't be able to see that common factor. So let's distribute the numerator. So root x times root x is going to be x, plus square root of x and minus square root of x cancel out. Then negative 1 times 1 is minus 1. So you can see that common factor of x minus 1, so I'm going to cancel out that common factor of x minus 1. That leaves me with the limit as x approaches 1 of 1 over square root of x plus 1. Now that we have fully simplified, let's try direct substitution again. So that will give us 1 over the square root of 1 plus 1, which gives us the real number 1/2. And because direct substitution resulted in a real number, 1/2 is our final answer, so our limit is equal to 1/2. Now for this next one, again, you should always try direct substitution first. So if you direct substitute 2, you get a 0 in the numerator and a 0 in the denominator. Remember, a 0 over 0 is handled a lot differently than any other number over 0. So I'm looking at that numerator, and that numerator does look pretty factorable, so I'm going to go ahead and factor the numerator. So I've got the limit as x approaches 2 of, I'm going to start by factoring out that greatest common factor of x, so I will get x squared minus 6x plus 8. And I've got that divided by square root of x minus 2. And I'm going to factor the numerator as much as I possibly can. So I have the limit as x approaches 2 of x times two numbers that multiply to 8 and add up to minus 6 are x minus 2 times x minus 4. And then while I'm at it, I'm going to rewrite that square root in the denominator as parentheses x minus 2 to the power of 1/2. Now, the only way that you can outright cancel out common factors is if they are exactly the same. Like this x plus 1 was exactly the same as this here. We don't have anything here that is exactly the same. However, these two do look similar enough that they can at least simplify. But because this has an exponent of 1 and this has an exponent of 1/2, they can't outright cancel out. But what we can do is recognize that these are two exponentials of the same base. So if you remember your quotient rule for exponents, if you have two exponentials with the same base that are divided, you can simplify by subtracting their powers, top exponent minus bottom exponent. This is basically that same rule, just slightly more complicated. This time, your base is going to be x minus 2. So I'm going to take these two, and I am going to simplify by subtracting their powers to give me x minus 2 to the power of 1 minus 1/2 is 1/2. And then everything else stayed exactly the same. So now that we have simplified this, let's try direct substitution again. So I'm going to plug 2 into every single spot I see an x. So I have 2 times 2 minus 2 to the power of 1/2 times 2 minus 4 equals 0. 0 is a real number. You can't have a limit come out to 0. That means the y-coordinates are approaching 0 as x gets closer and closer to 2. So, because that is a real number, your limit is equal to 0. Now, for piecewise functions, I will say that direct substitution can work for any type of function, but for piecewise functions, if the limit is one-sided especially, you need to figure out what piece you're supposed to direct substitute into. Don't just direct substitute your number in for, every single part and make a complete mess out of this. Figure out what piece that value would actually fall into, and then direct substitute only in for that piece. So you should only be direct substituting into one part of a piecewise function at a time. If you have a one-sided limit at one of those breaking points, then you are going to be direct substituting into the appropriate part of a piecewise function. If you have a two-sided limit at a breaking point, unfortunately, you are going to have to find the one-sided limits individually. So if you have to find the limit as x approaches a breaking point from both sides, you do have to use direct substitution into each piece one at a time, find the limit on the left and the limit on the right. If the limit as x approaches a from the left equals the limit as x approaches a from the right, then the overall two-sided limit exists and equals that number. If the limit from the left does not equal the limit from the right, then the two-sided limit does not exist. So what we're going to do is we're going to take this piecewise function. It behaves like the line negative 2x plus 4 if x is less than or equal to 1. Then it behaves like the radical function square root of x minus 1 if x is greater than 1. And what we're going to do is we're going to be finding the limit at that breaking point 1. So for the limit as x approaches 1 from the left, coming from the left of 1, values to the left of 1 are values that are less than 1. So we are going to be direct substituting, but we are only going to be direct substituting into this top piece, because this top piece is defined for values that are less than 1. So I'm going to plug 1 just into the top piece. So I have negative 2 times 1 plus 4, which gives us a left-hand limit of 2. Now for the limit as x approaches 1 from the right of f of x, values to the right of 1 are values that are greater than 1. So the piece that's defined for x's that are greater than 1 is actually this bottom piece. So to evaluate this limit, I'm going to direct substitute, but only into the bottom piece. So I'm going to have the square root of 1 minus 1, which is equal to 0. So because the limit from the left does not equal the limit from the right, then the limit as x approaches 1 from both sides does not exist. Now, direct substitution can work for trig functions as well. Just keep in mind that if you get a 0 over 0 or just some other 0 in the denominator, what you can use is trig identities and maybe a little factoring to manipulate the function so that you can evaluate the limit algebraically. So I will say that most of the 0 over 0s at this point in the course, when they involve trig functions, can be fixed by factoring. You just might have to use a trig identity. But no matter the type of function, even if they are trig functions, you should always try direct substitution first. So we're going to evaluate each of these limits using direct substitution. And I will say that in this course, unless a problem specifically says that theta or x is in degrees, the default is radians. So because it doesn't say degrees, these are all in radians. So we've got the limit as x approaches 0 of sine of x. Let's do a little direct substitution. We will get the sine of 0. The sine of 0 is equal to 0. You do need to know the unit circle, and you do need to know basic unit circle values. I will post a unit circle handout on Canvas. So then for this next one, the limit as x approaches 0 of cosine x, we're going to direct substitute. So we're going to have the cosine of 0. The cosine of 0 is equal to 1. Now for this next one, we're going to find this limit algebraically. So again, any sort of limit, you should always try direct substitution first. So for the sine squared of 0, we get 0. Over 1 minus the cosine of 0 is 0. So an initial direct substitution gave us 0 over 0, and I hold me to that promise at this point in the course. These can be fixed by either factoring or rationalizing. Since there's no square roots, rationalizing's out, which means we're going to be factoring. Now, in order to get a common factor to cancel out, you really do need to have everything written in terms of the same trig function. So we've got a mixture of sines and cosines, so we're going to have to rewrite something here so that everything is in terms of the same function. I am looking at this sine squared. There is a way to rewrite sine squared in terms of cosine squared, and that is going to involve the Pythagorean identity, cosine squared of x plus sine squared x equals 1. If you were to solve this for sine squared, you would get that the sine squared of x is equal to 1 minus cosine squared. So this is how you would rewrite sine squared in terms of cosine squared. So that's what I'm going to do. I am going to replace that sine squared of x with 1 minus cosine squared. And then I'm just going to leave the denominator alone as 1 minus cosine of x. Then, again, direct substitution does still give a 0 over 0, so we will have to do some factoring. The numerator is actually a difference of squares because 1 is a perfect square and cosine squared is a perfect square. So you're going to factor it like you would any other difference of squares. It's going to factor as 1 minus cosine x times 1 plus cosine x. And the denominator actually doesn't factor, but I am going to put parentheses around it. Then, now that we have factored and written this as multiplication, now we can cancel out common factors. Hey, there's a common factor of 1 minus cosine x. Let's cancel those out. So then that gives us the limit as x approaches 0 of 1 plus cosine of x. Now that you have simplified, now let's try direct substitution again. So we have 1 plus the cosine of 0. Cosine of 0 is 1. 1 plus 1 gives us a final limit of equal to 2. So, limits that involve trig functions might involve using trig identities. Now, not all limits involving trig functions can be done in this way. This can really only be handled with a 0 over 0 is really the only one that can be handled using factoring or rationalizing. If you have some other indeterminate form that's even worse than this, you can't use factoring or rationalizing. One technique to work with that is what is called the squeeze theorem. So the squeeze theorem works with very specific scenarios. So let's say that you have 3 different functions, f, g, and h. And every single y-coordinate for g of x is strictly bound between some other function f of x and h of x. So every single y-coordinate for g of x, without exception, is between f of x and h of x. And if you were to take the limit as x approaches a of f of x and the limit as x approaches a of h of x, and let's say that the limits of the 2 outer functions come out to the same value L. Then, because g of x is always bound between f and h, and the 2 outer limits came out the same, that means that the limit as x approaches a of g of x is equal to that same value L. Like I said, the squeeze theorem is used in very specific scenarios. This is one of them. So we're taking a look at the limit as x approaches 0 of x squared times the sine of 1 over x. Well, first of all, if you were to direct substitute, this is all kinds of a mess. You would get 0 times the sine of 1 over 0, so it would be 0 times the sine of something undefined. This is just all kinds of indeterminate, so we're not even going to try the direct substitution route. Also, no amount of factoring or rationalizing is going to save us here. But what I have by the picture, the graph of x squared sine of 1 over x is actually what's graphed here in black. And it does look like it is oscillating, but it is oscillating less and less till you get to 0. And it looks like the limit might come out to 0, but we're not sure because we can't see just how much it oscillates. So we don't know if this is just oscillating forever or if it is actually approaching 0. But if you take a look, every single point on that graph is strictly bound between this pink graph, x squared, and this blue graph, negative x squared. So this would be a situation where squeeze theorem could be used. We have this function. Every single y-coordinate is strictly bound between two outside functions, x squared and negative x squared. And if the limits of the outside functions come out to the same value, that means the limit of that inside value must also equal that same value. Now, here's the issue. If you don't have a picture like this, which you won't on an exam, here's how to figure out what those two outside functions would be. Let's take a look at this function. What part of this function is always bound between two values? Well, sine of x is always bound between -1 and 1. However, we're not looking at the sine of x, we're looking at this x squared times the sine of 1 over x. So what I'm going to do is I'm going to take this three-sided inequality and I am going to turn this middle function into x squared sine of 1 over x. Remembering that whatever you do to one part of an inequality, you must do the same thing to all three of them. So, because the reciprocal of 1 and -1 are themselves, that means that the sine of 1 over x is also bound between -1 and 1. Then I'm going to multiply all three parts of that inequality by x squared. So -1 times x squared is negative x squared. Then my middle function is going to be x squared sine of 1 over x. And then for my outside function here, 1 times x squared is x squared. So that is how, without a nice picture, you would be able to figure out what two functions it is always bound between. So what this means is that x squared sine of 1 over x is always bound between negative x squared and positive x squared. So let's take the limit of all three parts. A limit is like any other operation. Whatever you do to one part of an inequality, you have to do to all of them. So I'm going to take the limit as x approaches 0 of all three parts of this inequality. So I've got the limit as x approaches 0 of negative x squared. Then the limit as x approaches 0 of x squared sine of 1 over x. And then I have the limit as x approaches 0 of x squared. Well, you can actually use direct substitution for these two outside limits. So for the limit as x approaches 0 of negative x squared, little direct substitution gives that limit equal to 0. I'm going to leave this mess on the inside alone because that's what I'm actually trying to evaluate. So I'm just going to leave all that alone. And then I'm going to use direct substitution on this limit over here. So the limit as x approaches 0 of x squared is going to equal 0. So because x squared sine of 1 over x is always bound between x squared and negative x squared, and the limits of those two outside functions equal the same value, that means the inside limit as x approaches 0 of x squared sine of 1 over x must also equal 0. So squeeze theorem is used in very specific scenarios. So here's how to work with squeeze theorem problems both on your homework and on any exams. You start with the bounded part of the function, either the sine or the cosine. And then you build the inside function to look like the limit that you're supposed to find. Just keeping in mind, whatever you do to one part of an inequality, you need to do to all three. Then you're going to take the limit of all three parts of the inequality, and if the two outside limits come out to the same value, then that's what your limit is equal to. So that actually wraps up finding limits algebraically. Thank you all very much for watching. And then in the next part of the video lecture series, we're going to be looking at limits that are going to involve infinity. So thank you all very much for watching, and I will see you in the next one. Bye-bye.